The paper we're looking at today is SIMA 2, a generalist embodied agent for virtual worlds. This is a big one from Google DeepMind, and it feels like a major step in taking these massive foundation models from, passive text bots to active agents.
It's a huge jump. The core idea is that SIMA 2, which is built on Gemini, has been fine-tuned to really enhance its ability to move and plan and just act in all these different virtual worlds.
And we're not talking about simple controlled labs here.
No, not at all. We're talking about incredibly diverse open-world games. Everything from Valheim and No Man's Sky to something as chaotic as Goat Simulator 3.
And the results really speak for themselves. Quantitatively, SIMA 2 pretty much doubles the success rate of its predecessor, SIMA 1. But I think the bigger story is how it integrates high-level thinking-like planning and dialogue right into its actions.
That's the key. Its generalist capacity. SIMA 2 can handle complex instructions, and maybe most importantly, it shows it can generalize these skills to totally new environments it's never seen, even photorealistic ones from models like Genie 3.
And the thing that really points to the future here is the open-ended self-improvement. It can basically invent its own homework to get better at new skills, all without more human data.
Exactly. So this whole paper is really a validation, a proof that you can use these rich virtual worlds as a kind of scalable, safe training ground to solve one of the biggest problems in AI.
The embodiment challenge.
The embodiment challenge.
Okay, let's unpack that because it really is the classic starting point for this whole line of research. We are basically wrestling with a modern version of Moravec's paradox.
Right, which is just a fascinating observation. That's this idea that things we humans find really hard, like, playing chess at a grandmaster level or summarizing a dense legal document, are actually pretty easy for AI.
But the simple stuff.
The simple stuff is brutally hard. Low-level sensor motor skills, just smoothly pouring a glass of water, or in a game, walking through a cluttered room without bumping into everything.
And for these huge foundation models, the LLMs and VLMs, the problem is obvious when you think about it. They're trained on the internet. It's all static, passive data.
Their brains in a jar. They have this incredible world knowledge, but zero lived experience of doing anything. They're fundamentally disembodied.
And that leads to, terrible performance when you try to put them in a body, virtual or otherwise. They can tell you the steps to clear a dinner table, but they just can't execute the movements.
And that's where SIMA 1 came in. It was kind of the first proof of concept that you could even build a generalist agent that worked across a bunch of different 3D games just by looking at pixels and using a keyboard and mouse.
But it was brittle. SIMA 1 was great at short, direct commands. Go there, pick that up.
Super brittle. It couldn't talk back. It couldn't really reason about why it was doing something. And if the world changed even slightly, it would just fail.
So SIMA 2 is the answer to that brittleness. It's about shifting from just reacting to the world to actually being an agent with goals and plans.
Exactly. Less of a simple instruction follower, more of an interactive partner that gets what you're trying to do.
So let's look at how they built it. SIMA 2 is built on Gemini specifically, the really fast Gemini flashlight model. How does it actually connect to these game worlds?
This part is crucial. The interface is unprivileged. The agent sees and acts just like you or me. The input is just a 720p video stream, pure pixels.
And the output, how does it act?
The output is a structured text command that maps directly to a standard keyboard and mouse.
And that's a huge action space, right? It's not just WASD.
Oh, it's vast. We're talking 96 keyboard keys, plus mouse clicks, plus mouse movements. You have to think about all the things you do in a modern game moving, managing inventory, crouching, crafting, using menus. You need all those keys.
And it gets no hints, no secret GPS coordinates or object lists from the game engine?
Absolutely none. It navigates the world purely based on what it can see in the instruction it's been given.
Which brings us to the training data. This is a really sophisticated pipeline, starting with just raw human gameplay.
Yeah, they used two main methods here. The first was pretty standard. Single players recorded their gameplay and then, after the fact, wrote down what they were trying to do.
But the second method sounds more interesting, this setter-solver setup.
That's where they really tightened the causal link. You have two people. The setter gives a live instruction, and the solver executes it right away.
So the language instruction comes just a few seconds before the action.
Exactly. It creates this super tight causal connection. The agent learns that the words cause the action, which is so important for avoiding weird correlations.
And then comes the secret sauce, the thing that really separates SIMA 2 from its predecessor, the bridge data.
The bridge data is, I think, the conceptual breakthrough. It's synthetically generated using Gemini Pro, and it's basically the agent's internal monologue. It interleaves high-level reasoning with the actual low-level keyboard commands.
Can you give an example of that?
Sure. So a high-level goal might be, I need to build a shelter. The bridge data would then spell out the steps. Okay, first I need wood. I'll equip my axe. That's the E key. Now walk to that tree. WWW. Now, left mouse click to chop.
Wow. So it explicitly teaches the model how to break down a big, abstract idea into thousands of tiny, concrete actions. It's the bridge from knowing to doing.
That's a perfect way to put it. And then, only at the very end, they use a bit of reinforcement learning to fine-tune the policy on tasks they can easily verify. It's this whole stack that gives SIMA 2 its new capabilities.
Which brings us to the payoff. Because SIMA 2 is still a Gemini model at its heart, it has all that world knowledge and conversational skill, but now it can apply it, which opens up some really cool interactions.
The embodied dialogue is probably the best example. The agent can literally have a conversation with you while it's performing a task. It feels less like a tool and more like a co-op partner.
That sounds amazing. What does that look like in practice?
So imagine you're in a game and you ask the agent, hey, can you go check out those big egg-shaped things over there and tell me what they're made of?
Okay, so that's not just one command. That's navigation, identification, and reporting back.
Exactly. And the agent's internal reasoning understands that. It thinks, okay, locate the objects, interact with them, read the text, and then reply. So it goes over, looks at the on-screen text that pops up, and then says back to you in natural language, I found the objects. They appear to be plants containing carbon.
That's incredible. It's using information from the game's UI to answer a complex question. You see that same kind of reasoning in simpler tasks too, right? Like the ripe tomato house.
Yeah, that's a classic one. The instruction is go to the house colored like a ripe tomato. The agent doesn't have a picture of that house. It uses its base knowledge.
It reasons. Ripe tomato equals red.
Right. It internally thinks ripe tomatoes are red. I see a red house down the street. That must be the target. That kind of interpretation was just impossible for SIMA 1.
And this language fluency goes beyond English, too. They tested it with instructions in French, Mandarin, even emoji.
Yes, and it also lets it tackle these really long multi-step commands. There's one example where the instruction is something like, go to the second floor, turn left into the room with the tentacle, then go to the end of the hall and get the VR headset.
Which requires breaking that whole narrative down into a sequence of sub-goals it can actually execute.
All based on visual cues. And it's not just language, it can take visual prompts too. Multimodal prompting.
So you could show it a picture.
You could give it a sketch of an object from a game wiki or something and say, interact with this in the right way. They showed it a drawing of a tree from Valheim, and it didn't just walk up to the tree.
It knew what to do with the tree.
It knew. It equipped an axe and started chopping it down. It's seamlessly blending visual data, language, and action.
Let's get into the hard numbers, the performance metrics. In the environments it was actually trained on, how big was the jump in performance?
It was dramatic. Across the board, SIMA 2 basically doubled the average success rate of SIMA 1. It's getting much, much closer to human-level performance, even with strict time limits.
And you see this across most skills, like navigation and object management. But there was one area where it still really struggled.
Combat. Combat remains the really hard problem for these kinds of agents, especially when they're trained with imitation learning.
Why is combat so much harder than something complex like crafting?
It really comes down to the motor control. Combat often requires incredibly fast, split-second decisions and movements. Imitation learning is pretty good at teaching a slow, deliberate sequence, like a 30-second crafting recipe.
But hunting a moving deer in Valheim is a different beast entirely.
A totally different piece. You have to crouch, you have to lead the target, judge the arrow drop, and time the release perfectly. All that subtle noise in the human demonstration data makes it almost impossible for the agent to learn that one specific, perfect action. It's a huge open challenge for the field.
That makes a lot of sense. It's like the difference between learning a slow dance and a lightning-fast martial arts move. But this is where it gets really compelling. What about generalization? How did it do in games it had never, ever seen before?
This is the real acid test for a generalist agent, and frankly, it did incredibly well. Quantitatively, it beat SIMA 1 by over 10% in unseen games like Aska, and more impressively, in the MindDojo benchmark, which is based on Minecraft.
And that MindDojo comparison is a big deal.
It's a huge deal. SIMA 1 could only handle about 2 types of tasks in that whole suite. SIMA 2 successfully completed tasks in 26 out of 50 categories. That's a massive leap in breadth. It shows it's transferring abstract skills from one game to another.
The qualitative examples are maybe even more powerful, like the game The Gunk.
Right, which is this story-driven game with a really unique core mechanic, a kind of handheld vacuum cleaner device. SIMA 2 had never seen anything like it.
But it figured it out.
It figured it out by reading the on-screen text prompts, like absorb and hold. It understood, okay, this is a tool, and the visual feedback is telling me how to use it. It just generalized its concept of tool use to a completely new thing.
And this generalization even extends beyond video games into photorealistic worlds.
This is the really exciting part for robotics.
This too.
They dropped SIMA 2 into these novel, urban, and natural environments generated on the fly by the Genie 3 world model. These worlds look real, not like a stylized game.
So it learned how to navigate in a game like Valheim and could immediately apply that to walking down a realistic city street it had never seen.
Exactly. This is probably the clearest sign yet that you can use these diverse virtual worlds as a training ground, and that there's a real, feasible path to transferring these skills to physical robots.
Okay, let's zoom out a bit. When you fine-tune a massive model like Gemini on a very specific task like this, there's always a huge risk of something called catastrophic forgetting. Does teaching SIMA 2 to be a good gamer erase its general intelligence?
That's the central tension, and a lot of previous work has shown that, yeah, it can. You can train a model so hard on action data that it basically forgets how to have a conversation. You get a great controller, but a dumb agent.
But SIMA 2 managed to avoid that.
It did. And it's because of that carefully mixed data set. The human data, the setter solver, and especially that synthetic bridge data. They managed to keep the core intelligence of Gemini intact.
You can see that in the benchmark numbers, right?
Yeah, you can. On things like coding benchmarks, math problems, complex STEM reasoning, they only saw pretty minor drops in performance, maybe a 4% dip on coding, 16 to 25% on the really hard reasoning tasks.
Which is a crucial finding. It means you don't have to sacrifice general intelligence to get high-level embodied skill.
You can have both. SIMA 2 seems to be at this kind of optimal trade-off point between general smarts and specialized physical ability.
And they even found a way to get the best of both worlds for really long, complex tasks using a hierarchical setup.
Right, so SIMA 2 itself is based on the fast and flashlight model because you need speed for real-time interaction. But for the high-level planning, they use a separate, more powerful Gemini Pro model.
So the big, slow brain does the thinking, and the fast, nimble brain does the acting.
That's the idea. Gemini Pro breaks down a really complex instruction into a list of simpler subtasks. And then it feeds those simple tasks one by one to the low-latency SIMA 2 agent for execution. It's like a manager delegating to a specialist.
Which allows for things that would just be impossible for a single agent, like following a complex crafting diagram from a wiki.
Yes. The combined system can look at a picture of the Valheim campfire guide, figure out what resources it needs, go get them, equip the right tools, and then place the object, all while telling you what it's doing.
They even pushed it to test abstract reasoning applied to action.
Yeah, the meta-instruction test. They told the agent, from now on, do the opposite of what I tell you. And it worked. It successfully applied that abstract rule to everything it did next navigate, using menus, everything. That's high-level symbolic reasoning directly influencing motor control.
This brings us to what might be the most profound part of the paper. Open-ended self-improvement. Moving the agent from just following our orders to actively teaching itself.
This is so critical. You can't have human engineers handcrafting rewards for every possible task in a new open world. It just doesn't scale. So they built a system with 3 foundation models working together.
So you have SIMA 2 as the agent. What are the other 2?
You have a Gemini-based task setter. Its job is to invent new, achievable tasks for the agent to try. And critically, it looks at where the agent is weak and creates tasks specifically to help it improve in those areas.
And the third model handles scoring its performance.
Right. A Gemini-based reward model. This thing acts like a universal judge. It looks at the agent's attempt and gives it a score from 0 to 100. Anything over 50 is a success. This is a huge deal because it means you don't need game-specific code to check if a task was done correctly.
And this self-improvement loop actually worked.
It did. They tested it in the held-out game NSKA. And over multiple iterations, the agent's performance just got steadily better and better all on its own.
And it wasn't just getting better at things it already knew. It was learning totally new skills.
Totally new skills. It eventually got better than the human baseline on the test tasks. And along the way, it figured out things like how to put out a campfire, or how to find a rain collector, things that weren't in its original training at all. It was building its own curriculum.
It's just incredible. It feels like a real validation that you can have these agents autonomously adapt in new worlds just by generating their own experience.
It really is a foundational piece of research. It shows a clear, safe, and scalable path for fusing that high-level reasoning with robust physical control, which is what you need for general-purpose agents and eventually for real-world robotics.
But of course, it's not solved yet. What are the big limitations that are still out there?
Well, a few big ones. Long horizon planning is still a challenge, thinking on the scale of weeks, not minutes. And the agent has a relatively short memory. That's a hardware and architecture limit. You need a small context window to keep the interaction fast and responsive.
So it might forget the overall mission while it's focused on a small subtask.
Exactly. And like we talked about, that very precise low-level motor control, especially in chaotic scenes like combat, is still a really hard open problem for the entire community.
But when you combine this idea of an infinitely learning agent like SIMA 2 with an infinitely generated world like one from Genie 3, you get this really mind-bending possibility.
You really do. You have the ingredients for a truly open-ended algorithm. Something that could just keep generating novelty and acquiring new skills forever, bootstrapping its own intelligence.
Which leaves a pretty big question for everyone listening, especially for the researchers and engineers out there.
It does. If you had an agent like this, one that could constantly improve itself in any virtual world you put it in, what is the one complex multi-world task you would assign it? What challenge would you give it to ensure it continues to innovate and teach itself new, useful skills, potentially forever?